automotive application. Those about. And rest of industrial application, it will be talked in the next lecture. So a new generation composite application means it's the most important keyword is weight. All kinds of composite materials can provide the benefits of weight saving. It's a very basic one. But even in the case, those are not losing any stiffness or strength. And in order to that, have best the design, the satisfaction, we can design its anisotropic property as we wish. So we can remove any stiffening along the directions where we don't want to have a high stiffness, high strength, something like that. So those three different kinds of advantages are basic keywords for all kinds of composite materials. So it can be summarized like this, offering unparalleled strength, weight saving, and design flexibility. It's based on those three characteristics. So here we'll explore the next generation composite application. So we start from aerospace application because it is first use, usually first use with advanced technologies, not just the material sector, but also all of very sophisticated, newly developed one. If those are very reliable, then regardless of the cost, all of new generation technologies can be used for aerospace. So that's why all of advanced technologies can be found in aerospace application first. So then that doesn't mean automotive application is less technical, less advanced technique compared to aerospace. So I think the extension to the automotive application after aerospace application has more meaningful, because aerospace application case, so it is not considered for mass production because the number of required structures are limited. But automotive application case, mass production must be engaged. That means advanced technology is fully developed, and the cost can be lowered by mass production. So the application to the automotive engineering is very important to our daily life, I think. So aerospace application, so of course we are enjoying the lightweight structure and aircraft interior, advanced wings, fuselage impingement, those kind of things. So lightweight structure is the main body, right? So it's ultra lightweight airframe is the example. And aircraft interiors, the durability, design freedom, and weight savings. So usually we say this lightweight structure, ultra lightweight airframe, something like that, we say this is a primary structure. That means the structure must support very highly loaded the environment. But the other things, this interior ones, this we say is a secondary structure. Secondary structure means it not so high loading is considered. Okay? So that means it's just a durability or design issue, weight saving, those are important in this case. Okay? And advanced wings is important of course, but relatively to the primary structure, this advanced wings has smaller surface area. Okay? So, but it requires complex geometry. But as you see, the composite material manufacturing process, because mostly made by manual method, that means complex geometry can be the necessity. It can be embodied through this. Okay? So complex geometry and the integrated system characteristic is possible for the advanced wings by composite materials. And fuselage is also it's a lighter and more durable characteristic is the possible from composite material, and currently those are being built and used. And the infinite is a stability and the precision which can be satisfied through composite materials. So firstly, lightweight structure, primary structure for aerospace engineering is first as a high strength to weight ratio is important. So this kind of key issues is important when you choose composite system for use in design process. So composite material offer exceptional strength while being significantly lighter than traditional metals like aluminum alloy. Right? And secondly, the tailored design can be found through advanced composite materials. So composite can be engineered with precise fiber orientation. That means unneeded, unwanted directional the directional stiffness strength can be removed intentionally. So it can provide the more weight saving. So we can optimize the strength and weight for primary structure. And also this is the outermost surface used. So corrosion resistance is very important issue. So as you see, the composite material is also very strong against corrosion. So this is also the main point to be chosen for this use. So this is a sample of the currently used the composite materials in aerospace application. This is secondary, okay? Seating, and this storage part inside the cabin and the cabin interiors. Okay? All of those used by composite materials these days. Okay? And advanced wings, so the important points aerodynamic efficiency, integrated system, structural integrity. So of course this wing must require complex optimized shape. So that manufacturing the process must be considered to make this possible. And the integrated system, so composite wings allow for the seamless integration of control surface, sensor and other systems. And the structural integrity, it is very easy to embody strength and durability for aircraft wing and improving safety and reliability. Okay? And whereas for automotive application, so the current composite material application for airplane or space shuttle was a long story already. So it's going back to 1950s, 1950s, and mostly developed in 1960s. But it comes to the automotives. It just maybe going back to 1990s and most. So even these days, after 2010, these days are gradually increasing the number of applications for automotives. So most difficulty issue about that, of course, the difficulty of automotive manufacturing process for composite materials. Because only that can be guaranteed. The automotive component or body can be used, because automotive means it does not manufacture just less than 100 units, something like that. It needs at least millions, 10 millions, something like that, per unit component. So that means manufacturing issue must be considered for automotive application. That is a different point compared to aerospace application. So body panel is body panel. As the purpose is the same as the airplane, aerospace industry is. So body panel is it is used because it's lightweight, and in a little bit more important emphasis for automotive compared to the aerospace is impact resistant, because airplane case is a very small number of opportunities to be impacted. But the automotives means it is daily using one. So it means that there are many accidents. So we must think there are many small and big impact from exterior. So the final products of body, this is the exterior surface. It must be considered to have impact resistant material. Otherwise, it cannot be used. Right? And customizable body panel. So because as you see that these days car is very beautiful outer design, and very curved surface, very complicated. The very small part of design also can be found easily. So that means it must be the customized as needed. And the chassis component case, differently from the body panel, the size of components is relatively small. That means RTM can be used easily. RTM is one of the well-established manufacturing process for composite materials. So this so part of chassis components and some other small the auxiliary components is possible through RTM or its variations. And its emphasis point for use is must be about superior strength and stiffness and weight saving. So the weight saving is a very common issue for whenever we choose composite materials for raw material. But in this case, superior strength is different from body panels. So body panels, although it is a primary one, but the automotive structure case, the main load bearing part should be chassis. So chassis must have a superior strength over a body. And the stiffness also very important because it's a large deformation cannot be expected for automotive use. And recently the EV is very popular, very common, although these days are a little bit chasm of EV, but the number of EVs will be increasing continuously. And in the case of the E and the customization, as we saw the previous slide, so those are important. So this is a common emphasis. And the impact resistance, because this body panel is installed utmost of automotive. So it must be impact resistant to external incoming object. And the customization is for design issue. Okay? And chassis components is exceptional strength is required and improved stiffness is required. Exceptional strength is to transfer the load very well. It is needed due to that point. Improved stiffness, the large deformation doesn't want to. It is not wanted. It is not wanted because the stiffness, the chassis must be very robust and strong. Okay? So improved stiffness is kind of the Young's modulus or something like that. So it's very important for chassis components. Okay? And our weight saving is also important, even for conventional vehicles, because the power per unit, the weight should be high. It is mandatorily necessitated to be survivable on market, because in the case the fuel efficiency can be enjoyed. Right? And the EV case, EV battery enclosure is most important issue. Right? So EV battery thermal management, structural integrity, and design flexibility, three of those. And the thermal management is must find the characteristic of effective thermal insulation characteristic and cooling, the integrated cooling system needed from the composite materials chosen, so that it can optimize the battery performance inside. And the structural integrity issue is regarding exceptional strength and resistivity points. So this kind of highlighted points should be basis to choose a composite system for automotive. Of course, all of composites in design pool for automotive. It must be possible, very easy or very effective for mass production. Without mass productability, it cannot be considered for automotive use. That is very different point from the aerospace application. And this composite body panel is so this improved aerodynamic and weight reduction. So this is the airplane, the head part, and the streamlined design, weight saving, corrosion resistance, and customization. So considered and streamlined designs mold into complex aerodynamic shape. It's mandatorily needed, right? It's so that it can it can so make very high speed traveling in the air. Right? And the overall weight should be very small. And of course, the long-lasting performance is very important because the differently from automotives, it's the lifetime should be very long, longer than decades. But automotive case mostly within decades. And the composite chassis component, so it's used to enhance durability and crash protection. And the crash resistance is needed to absorb and dissipate impact force. So aramid fibers reinforced composites, especially have high the impact resistant materials. And structural integrity is more robust, and the durability issue should be satisfied. And EV case, thermal management safety means thermal regulation and the impact protection and weight optimization. These three issues will be design points and currently being used based on these the point satisfaction. And thermal regulation means a composite battery includes incorporate advanced thermal management system, so as to maintain optimal operating temperature and prevent overheating. The impact protection, the high strength of composite ensure the battery includes that it can withstand significant impact and collision, safeguarding the critical components. And the weight optimization is a lightweight composite material help minimize the overall weight of battery system. So many students, they just think maybe the electric vehicle is lighter than traditional vehicle. They think like that, but opposite, right? Opposite. So because electric vehicle is much heavier than traditional vehicle, electric vehicle must have larger contact area tire field compared to conventional ones. It is not due to the body weight. It is due to weight of batteries. Battery very, very heavy, and to cover up to 500 kilometers per full charge condition, the battery weight itself is already 300 kg, 400 kg, so that they wanted to use aluminum alloy for body to reduce overall weight. Okay? That's why electric vehicles have many aluminum alloy component and bodies compared to traditional ones. Traditional ones, high strength steel plate is needed to use usually. So whenever possible, the electric vehicle, they wanted to get much weight saving. So composite material is one of the best choices. But cost is problem. Still, cost is problem. And the manufacturing process for composite component is an automotive lathe ATL system. You heard the last lecture. And the molding techniques and the curing finish quality inspection. For automotive use, this must be automated. Otherwise, mass production is not possible. It's not possible. So, this manufacturing process for automotive composites. As injection molding is mostly used, and compression molding is also used for large body structure, and RTM and automated fiber placement is AFP, automatic machine. Those are already developed and can be found on markets. But in the last lecture, maybe I did not talk about compression molding. So compression molding is very simple one, so I just add one more slide here. For manufacturing technique for composite materials. This compression is like the conventional press compression machine. It's the same. But in this case, it is not used for metal raw material. In this case, we are talking about composite panel. It should be the body must be heated before placing between compressed mold. So curing oven, so this is a heat schedule that's needed before pressing. Because the ambient temperature is not good temperature for making permanent shape change in composite panel. So it must be heated by using some heat schedule. So that means it will be pressed as a final shape. That means that in this case, this matrix should be thermoplastic case only. Only in that case it can be compression molding method can be used. So thermoplastic PMC plate will be used for this purpose. And the quality control and testing for composite structure as material testing, structural evaluation, environment testing is being engaged. And environment testing, this is the needed for composite material part. It's different from the metal part for conventional vehicle compartment, because this composite material is a matrix. It means the binding material. It's a plastic mostly. Plastic is humidity absorbing and UV light influenced, so its property can be degraded sooner or later. So it should be tested in outside and in some very designated environment. It must be tested. It is different issue compared to metal components of conventional components. And the maintenance and repair composite aerospace parts. So inspection is visual and NDT usually is needed. So steel case, because it has very good ductility, its plastic behavior after deformation is guaranteed. So its toughness is well enjoyed already. So there is no issue about that. But composite material case, it can be fractured, sometimes brittle. So damage distribution is very concerned. So non-destructive inspection technique is very, very important in composite material manufacturers. So all of composite material manufacturers for final use, they must have a very expensive NDT equipment. So there is no other. just a visual inspection is primary. It is not sufficient for inspection. And the damage distribution status must be checked before sending it out to the market. And the repair technique is very complicated and important issue. So metal case is very easy to repair because it can be reworked plastically, and it can be welded if needed easily. But composite material case, it is not possible. Welding, it is not possible. And if there is some laminate inside, partially damaged or delaminated, then how it can be fixed? It's very difficult issue. So repairment of composite panel is a special technique to entrepreneur. So that kind of a fixing repair technique is going to, it should be asked to very specialized industry, not by workshop easily. Because although it can be the bonded again, for example, by yourself to repair some the detectable damage, but if you check it very microscopically, then the stiffness or strength have not been repaired, has not been recovered completely. So you cannot believe after very simple bonding by yourself. It must be asked to specialized company. Okay, must get specialist advice. Otherwise, you may get final catastrophic failure. Means death. So it's very important. Right? And so a repair technique is one of a very good business points. You can think about that. How, so rather than manufacturing, I repeatedly said up to this lecture, composite materials in the sense of mass use in community is the beginning stage. Although it has been introduced into industrial structure more than 50 years ago, but it is just for small number of applications. But recently, the mass use of mass production based components or parts with composite materials are just the beginning stage. So all kinds of related business now being founded. So you can participate in those kind of technical business chances. So if you get any composite design part or the reinforcement or matrix parts or manufacturing parts or repair parts, any kinds of parts related to composite material. So there are tremendously many opportunities you can start your business. But based on the terminology used in this society, in this community, must be educated by yourself or through any kinds of education, so that you can communicate with the specialists in the community. Because that kind of participation is very important, because every day new idea and new trial and the new patents are being developed and introduced. So there are so many variations. not so difficult, but most time consuming and cost consuming. So you should choose one of the good one too. The repair technique is one of those. Okay? So the repair methods such as patching, bonding, reinforcement, those kind of is one of the issues. And preventive maintenance. This is a proper maintenance protocol. Also, this is well trained. This must be conducted daily or weekly, in regular manner. The cleaning, lubrication, protective coating. This can help to extend the service life of compressed material. And the sustainability and the recycling of compressed material. So material recovery issue. So innovative recycling process. The recycling, this will be treated tomorrow at the last lecture. But material recovery is one of very important issue these days. This is mandatorily necessitated by government policy in many countries. So although it's more costly and more troublesome to compressed material manufacturers, but it cannot be avoided. It should be practiced. Right? Innovative recycling processes are being developed due to policy issue and eco-friendly or zero carbon dioxide issue, many kinds of things. And being developed to recover and use valuable fiber and resin from the composite part. And repurposing is used differently. Right? So composite material can be reclaimed, repurposed for a variety of applications. So as we wanted to get waste reduced and sustainability promoted. And the closed-loop manufacturing is the issue we treated tomorrow. But any closed-loop manufacturing is one of the common the manufacturing issue, the full life the loop for any kinds of industrial product. These days they consider recycling from the design stage. And sustainable manufacturing, as a composite can be produced using renewable recycled material, reducing environmental impact. And the end of life recycling, improved efficiency, those will be treated tomorrow. Right? And the automotive industry trends and challenges is lightweight construction, sustainability, and customization, structural integrity, and design flexibility. So those are the important to engineers and operators. So lightweight construction is especially for small and large scale mobilities. So every kind of mobilities that require this kind of advantage. And the sustainability, so automaker under pressure to use more environmentally friendly material. So otherwise they cannot sell their vehicles. So it should be accepted as by the authorities or by the consumer groups. If any manufacturer gets a bad reputation about this, to violate sustainability or against the eco-friendly environment issue. In the case that manufacturer is difficult to survive in market. So although it is costly, but it's willing to accept those kind of mission. Okay? So composite material also not exempt from that issue. And the customization is various design, different design and the design variation is accepted by users. The final consumers these days, they request a very unique color or unique shape sometimes whenever it's possible. So manufacturers may be able to offer those kind of various options from final users. So composite material manufacturing engineer must think those kind of flexibility too. And the structural integrity. And the composite can be engineered to provide exceptional strength and rigidity and meeting safety standards. It's well understood. And the design flexibility is a composite or complex organic shape cannot be achieved with traditional manufacturing. So, one of misconceptions based on new materials. So conventional manufacturers, traditional manufacturers, if they want to get, okay, so weight saving is needed, although it is a little bit more costly. But many times they do not understand the manufacturing step should be very changed, even for monolithic cases. Okay. If that component changes from metal to ceramics, for example, except composite material case. Even in the case, the shape of the component, they just think that shape of component is just kept same as metal or ceramic. But processing method is different for metal and for ceramics. One is just die casting or just a conventional casting, sand casting. There are many conventional ways to manufacture metal components. But if you adopt the ceramics, in that case, those kind of manufacturing technique will not be used any longer. Right? So it's different. That means there's no casing. I mean, no mold. Right? It's kind of a CVD, some different technical method will be applied. That means the shape can be changed. Final shape. For example, if it was not easy to satisfy design requirements based on metal due to its manufacturing process. In the past, maybe because of processing technique, that design shape must be accepted. But if they change material to others and the manufacturing method is changed, then that unnecessary design part can be omitted or changed. It does not need to be kept as the same shape. Right? Not just weight saving, the design requirement should be investigated. If you change material for the same component. So composite material case is also considered for the better case, because monolithic materials does not provide anisotropic design. But based on composite materials, you can intentionally design on isotropic characteristics. So you could, the stiffening only direction you want to do. If any direction has no strength needed, then you can neglect the stiffening for that direction. That means design flexibility much vastly better to the case of composite material. So you must think those kind of issues. The design flexibility is not just for the basic area. It must be think in advanced way. And this is a real case study. The real world composite automotive applications are already being used. The lightweight race cars, there are many Formula One racing, something like that. Based on the same engine power, if you get very light outer body, in the case the competitiveness should be enhanced. So lightweight race cars can be found already. By using composite materials, you can enable ultra lightweight, high performance vehicle as final function. Right? Already these kind of things are used. And efficient electric vehicles, by using composite materials, you can maximize the range and the efficiency of vehicles, especially the battery case, as I said. Right? And premium automotive design is possible from composite materials. In the case, body painting is not needed. Right? Because body painting needed for the cover, the base color. But the metal case is needed. But engineering plastic, so all of color is already decided. Right? So painting job is not needed. And the future composite in automotive industries, so they are consider increased adoption of composite materials because it can guarantee a wide range of automotive function. And innovative manufacturing, they are thinking, because mass production must be possible to use composite materials. Otherwise, mass production capability, composite material cannot be used. But the performance of composite materials already proven through aerospace industries. So to get weight saving and higher strength, that means higher specific strength through composite materials. So many of automakers, they want to use composite components these days, but they must resolve how make it automated manufacturing technique. Otherwise, mass production is not possible. Right? So innovative manufacturing is every day, always they are practicing and developing for application of composite material into automotives. And the sustainability focus. So metal case, the recycling is well established, but composite materials is not well established yet, but it is mandatorily required by authorities. So sustainability focus is very important issue for composite material components. Otherwise, they will get a bad reputation against the eco-friendly environment. So those are considered by the industries these days. So this is the application for the aerospace and automotive industries. And next one. as a renewable energy application and the biomedical application and sports and leisure applications. So before going into lecture 13, so do you have any question about the lecture 12? Any question or suggestions? No? So actually each lecture, even part of it, it is sufficient to issue for one semester. So it cannot be go into very detailed manner. So if you give any question, then maybe it will be very good to discuss together. So maybe through email or other method, you may contact me if you have any other questions in other time, right? Okay, let me go into the lecture 13 directly. Right? So this is just the same coverage of we have seen the previous lecture. This is different industry applications. So first, renewable energy application means from wind turbine blades and solar panels are typical ones for composite material application, and the biomedical application, then prosthetics, implants, wearable device is another typical topics. And the sports and the leisure application is a high performance bicycle or tennis rackets and the sports equipment. So where established the business sector through composite materials already. With me, even my case, I'm exercising by a cycle, and my bike is very expensive. I bought because it's a carbon frame. It's very expensive also. But even the low grade the bicycle these days, they just emphasize this carbon frame, although it has a less grade carbon fiber, something like that. But that means carbon fiber or other kinds of composite material application for sports goods are very daily life. So you can find everywhere, right? Let's see the renewable energy first. It's harnessing the power of wind. So blade design. Usually that blade is so for the one who doesn't see the interior this wind farm, then they don't understand how large it is. But I believe so many of you have already seen the real the electric power generator. Its height is the tens of so I mean it's almost 40 meters, maybe 50 meters. It's very, very high. And I have experience to engage in the brake system of a blade, this farm blade, this power generator kind of things. But it is very interesting the experience. But this length of blade is about 50 meters, 60 meters, 70 meters, something like that. This should be lightweight. Because sometimes in accident, this blade can be broken. Then you see that when very fastly rotating case, this tip speed is more than 500 kilometers per hour. That means you can expect how, if it is broken, how far it can be fly. It can fly. How far? And it's very critical to human lives. So anyway, this is needed to be very stiff, but very light. That means everybody can think, okay, composite material is one of candidates. Right? So conventionally, the aluminum alloy blade were used, but these days composite material blades are being applied. Right? And one of I had two PhD dissertation advisors. One of those the composite material specialist, and he engaged to develop the composite material blade. So I heard something about that from him, but anyway, it is not easy because this is very big composite material blade. Its uniformity very important. It's the three. The blade must have very same the uniformity. Otherwise, this will be eccentric, the rotating part. So it will make big problem. And blade design is innovative aerodynamic shape and lightweight, high strength material is needed. Okay? This because this can guarantee the turbine blade efficiency, and that can be well satisfied by using composite materials, polymer-based composite. So, and the durability. So cutting-edge composite materials enhance blade resistance to weathering and fatigue, and ensuring long-lasting performance. And the scalability and the development of larger, taller turbine harnesses, stronger, more consistent winds boosting renewable energy output. So this is very good application point by using composite materials, and the different kinds of the composite the combination may be able to be considered for different the design and different manufacturing, because the cost is very high. So cost and the performance should be well combined to develop this kind of blade. And there's a sun energy case. So it's a new solar cell material and the panel design significantly improved the conversion of sunlight into usable electricity. So for this, it should be the lightweight and the well functionality should be considered, right? So this is a backing material, and the cells, so the cell can be flexible. So it's kind of a composite material basis, and the panel, backing panel also is composite material is used. And this kind of case a little bit smaller scale of automotive or aerospace use, right? But it's coming to the area we are talking today. Is it's a reinforcement scale is down. Okay? And the prosthetic limb and the sensory integration, personalization is a robot arm. It's also one of the main the application of composite materials. And improve the quality of life if possible for medical use by using composite materials. In the case, the differently from the previous the large scale of composite material structure, These ones are usually nanoscale or microscale reinforcement are considered. So that means rather than continuous fiber, so this is a discontinuous reinforcement or randomly dispersed reinforcement should be considered and adopted, right? So CNT is carbon nanotube. Those kind of things are frequently used, or some other kinds of chemical particle can be used. So this is kind of biocompatible ones, biocompatible with the carbon nanotube or the reinforced. Okay? This is a carbon nanotube. So cardiac implant, neutral implant, also pedic implants, those look like monolithic material based, but to get more the efficient product, so usually composite, nanocomposite materials are applied because this should be put into human body. So if you get very heavy, then it is difficult to use, right? So, for example, this kind of the biomedical product, if this is very heavy, although it is well automated and well intelligent, then it cannot be used. For example, at the time of 2007 or 8, on those days, one of university in the United States, they developed the human limbs to compensate loss of arm or loss of leg. At the time, it can be moved. It's reported can move by using the nerve electric signal can be used to move this one. So it's very. But at the time, the one arm was 20 kg. So this one is very intelligently controlled by the patient's intention, but that arm is 20 kg. Then how it can be used? So after that, in 5 years or 6 years, they successfully reduced the weight by using a composite material like the lightweight material, and down to 6 kg. So, and I believe it's the more lighter these days. So it's adoptable now. So anyway, weight is very important, and the stiffness, moderate stiffness is important because human when you use any kinds of artificial leg or artificial arm, something like that, it does not support only static load. It should support impact, right? The dynamic load. That means for example, if your weight is the 50 kg, for example, in the case and the impact case, that instant load can be increased up to 7 times. Then be 350 kg in the case. So that structure must absorb those kind of impact in the case. So not just the less grade of stiffness, very high strength is needed. That means lightweight and high strength, high stiffness. What is needed? It is composite materials. So in biomedical parts, so different point from others. So in this case, in some interfacing part at least, or implant case, biocompatible is very critical issue. That means medical device, if it is the surgery inside the body or something like that, in that case, the authority approval is mandatory. So it means biocompatible must be satisfied. It's very important issue. So the development, the finish is takes very long time in those cases, and accordingly, the development cost is very high. So it at least 5 or 6, 7 years needed to develop one implant biocompatible device to get approval. Okay. So although it's very attractive area by using the composite materials, but from the personal the background, it is not difficult to be engaged. Most the big the company funded the project only possible for this case. But composite material, especially very advanced, the cost doesn't matter in the case. That doesn't. Okay. So if it is very well functioning, lightweight and biocompatible, then it will be very good contribution to patients. And this outdoor use for human activity this is just for health and fitness purpose. In the case we are using many sensor or actuator in this case, but those cases sensors, there are many cases we use composite materials also. And as I said, the sports goods already we can find many the devices that adopt composite materials already, because it's very lightweight enjoyed and good stiffness also can be obtained. And precision and performance in tennis, so lightweight, strength, vibration, dampening, and the spin and the precision, any kinds of mechanical or the material properties as well as the functionalities can be designed and choose from the composite materials. So composite material, we have already many kinds of many scale of reinforcement materials, and we have many matrix materials to choose. So there are tremendous many combination cases based on various reinforcement, various sizes, right? And the matrices. Okay? So by those combinations, if you can manufacture or try to make your own prototype, and it can be mass manufactured, in the case there are many chances to get the contribution to various fields. So, and the advanced materials, so this soul material also. If you if you mind on the soul material and the soul design of this shoes for sports purpose, then it has many stories. Although it is very common, but it is not. So because depending on different of exercise, the soul design should be different, and its mechanical property also different, and due to its manufacturing, mass manufacturing technique, the choice of material should be seriously considered. So even for this very conventional shoe, if it is expected to get some advanced function or support to someone to compete, in the case, there are many things to do as a composite material engineer. Okay? And integrated technology pushing limits to the users. So those kind of things are possible through composite materials. So biomedical advancement these days they strongly depend on the composite materials. And biomedical renewable energy, okay, so as a summary, it's a sustainable power source, increased efficiency, and environmental benefits are key points to be considered. And sustainable power source is the solar kinetic body heat to biomedical device, reduce reliance on traditional battery. And the renewable energy provides a continuous, reliable source of power, improving performance and lifespan of biomedical technology. Environmental benefit is renewable energy in biomedical application, because in the case the sensor actuation, those kind of need the power source. The power source, so maybe you can use battery inside. But rather than it, if it is self-harvested, it's better. You can use self-harvesting, so that the sensor, it has no battery. But from your body movement, it can have a mechanical impact, mechanical the behavior all the time during running or doing some activities. Then that kind of action can be source of the energy harvesting. So that sensor can be implemented into that the sensor. Then that sensor looks like permanently operating without any power, but the power is harvested, self-harvested. And the prosthetics, so for example, powering artificial limb, the solar-powered prosthetics, kinetic energy harvesting, and improved functionality. Those kind of things are issues considered in this application. So voltaic cell is embedded in prosthetic limb, convert sunlight into electricity to power advanced sensors. So you don't need to change by yourself. Right? And the kinetic energy harvesting case, the movement of prosthetic limb can be harnessed to generate electricity. So even in the case, you don't need to replace any battery by yourself. Right? So by using those kinds of the power or supply, you can make many kinds of self-actuating devices, the tiny small the bodies. If it is a large one, in the case a larger energy consumption is expected, but in this case very small one, tiny small one, so self-harvested one is sufficient to actuate these ones. So cardiac implant, neural implant, so improved patient outcome can be expected by using this sensor and the small device, the body design by using composite material techniques. It's very important area for application. And the wearable device case also is a renewable energy for health monitoring. So this kind of application, solar powered wearable, body heat generator, and the kinetic energy harvesting improved patient engagement. Those are key issues considered in this application. So it's similar to the biomedical device. These ones also you don't need, many times you don't need to worry about its power. And behind that, there are composite material design and products. And this harnessing kinetic energy, the powering process is the joint movement miniature generator power. So this kind of very elegant automated artificial leg or arm. So, and as a prototype, I forgot the name, startup company in the United States. I forgot, but there was very excellent the product invented there. So I heard he was TD. So TD in his address presentation, he displayed a very wonderful development. So I was deeply impressed after seeing the TV. But when I got to know the price of it, surprised, because it is not manufactured, mass manufactured. To make that prototype, it is $400,000 US. So who can use that? Who can use that? So seven years ago, about so one of surgeon the approach to me to develop possible development of cheap active artificial leg, so less than 10,000, because he said the motivation to him was he conducted many surgeries to diabetic patients in his clinic. So whenever they amputated their arm or the leg, their disappointment is very deeply sad. By that patient, he is very painful to see. So, but at the time, he said the government supported the artificial leg. It's very like a mannequin leg, something like that. It's no function at all. So it is already about 2,000 US in South Korea. So if any active, he saw the very the advanced artificial leg already. So if that kind of thing is very cheap, then moderately cheap, then it can be the hopeful to amputate the patient, he said. So so I asked one of my the PhD student. He's an Indian student. Then now he is working in my institution together, and I asked him to develop one. So the target is the market price is less than 10,000 US. So the running is not possible based on that, but walking is the actively is can support the amputated patient, conceptually. His dissertation was like that, and he made some prototype. It's well functioning, I guess, as he graduated finally based on that. But I used very simple to make weight saving. I used carbon composite. It's very light and stiff. And we wanted to memorize the type of walking behavior of that patient. So it means if he is, because still he has one another leg. So the foot pressure is normal pressure is already gathered. So this artificial leg can get some information by using piezo on the bottom of the foot, artificial foot. So through that we can collect the pressure distribution, and if we want to get some actuation. If he make the falsely the foot bottom is not placed on properly, then it can make automatically the right position. It can, so that she can walk smoothly like it's just so a prototype stage is just a few thousand is possible, but not a fully automated one. But what I thought at that time is, if someone wanted to develop something, as everything is very possible these days, because we did not research any sensor. We did not research any composite materials for that student case. It just integrate from the existing technologies. CFRP already there, and the sensor already there, and to test Arduino already can be obtained. So by himself, he can integrate all of interdisciplinary informations, and he can make it work. So it's a very good time to do some development or some contribution to the community. Any kind of thing. If you have motivation, then by conducting very basic investigation around you, then you can get to know that sensor is needed, that PCB is needed, that kind of structure needed, and the build is not so difficult. But if you wanted to make it final, the market product, then some money is needed, support is needed. But the basic concept embodiment is not so difficult. So I think most important thing is what are you, what inspire you. So what is your motivation, and are you willing to conduct any practice by yourself, and do you want to finish that purpose by yourself to the finish. So that kind of intention and action can do everything, because you don't need to develop your own sensors, right? There are many pressure sensors, there are many actuators, there are many choices of composite materials. But in the past, it's very difficult because sensor is a very small number of available, and the size is too big. But these days, MEMS devices, MEMS sensor, they are very cheap, just a few dollars or something like that. So you can make any kind of sensor, and that kind of data can be processed by using the openware found on internet before making it commercialized. So, so composite material is a very contributing technology, I think, because the weight is always problem. Weight, you know, if you develop something, the final stage difficulty comes from structure, because to make a structure, you cannot use wood for the purpose. If it is not composite materials, maybe the metal should be machined But to machine that metal into final shape, it requires cost. But composite materials, the pre-preg can be available. And that can be processed by yourself without big trouble. So by using the stacking the tape as you wish, you can make anything around the PVC pipe. We use the PVC pipe around it, pre-preg can be taping. And it can be heat treated at a relatively low temperature. Right? It is sufficient to see your own the design. Of course, the commercialized product are a little bit different story after that, but the composite material is very useful material to be applied even by yourself, because it is not need the machining like metal. And so capturing body states, this is another the energy the obtaining technique. So this can be used together with the composite material structure. Okay. And the solar powered wearables. And this advanced, the advancing remote healthcare is also possible. And challenge and consideration in biomedical renewables as power efficiency, miniaturization, safety, and biocompatibility, and the future material in renewable energy biomedical application. So also you can check after this slide. It's just a summary about what I said so far. The performance bicycle carbon fiber frame is very common these days. And rechargeable electric motor also. I have some the study about electric motor too. So I have experience to develop the power pack and the battery the pack and the electronic brake. The three different modules can make any kinds of mobility. Right? So what I think is so if we can make a very light motorcycle, in that case it is very usable or contributable to motor rider, because if it's a full-scale motor rider, not a scooter, in that case that body weight, total weight is heavier than 200 kg. 200 Harley Davidson full scale motorcycles, over 200 kg. But the mania on motorcycle for those kind of full size one, so they cannot enjoy that kind of motorcycle as they get older, because it is too heavy. So they cannot manage. They cannot manage that weight. So after 50 years old or 60 years old, they just give up that full scale. They just going down to scooter, something like that. But I think if we use composite material structure, in that case, I simply calculate then possibly the whole overall weight of a full size performing motorcycle, it's an electronic motorcycle. It's about 100 kilogram kg. It's possible in the case equivalent to scooter weight. So someday I wanted to build those kind of ones. So I developed a power pack and battery management system and the wireless electronic, and I got the part of it American USA patent. So I wanted to build those kind based on the composite materials someday. So so what I wanted to say is if you have some interest in the composite materials, because it can give you the much weight saving and high performing mechanical properties and the mechanical characteristics. So there are many things you can do. So this kind of series lectures it's not good to address about detailed technique for calculation or design issues, something like that. This is just for introducing what kind of issues are handled in this community. So that's this series lectures purpose. But if you have a strong interest toward something, then please consider about the use of any kinds of composite materials. Then you can maybe find something someday. So this kind of renewable energy source, solar-powered charging station, we can find these days in many places, but still there are many things to be solved still. So next in the next lecture we will think together about recycling. But the advantage of using composite materials and the possibility of existing the manufacturing technologies is already the size of useful to be adopted already. I think. So the day by day the new reinforcement material is being introduced into the market. So graphene, carbon fiber, or any other kind of natural fiber or natural reinforcement form can be found around. So far, I think we have all over understanding why composite material is seriously considered for the industries and any kinds of basic materials, but we don't know the details yet, because we are just having the conceptual ones only. But the most happiest one is that all of these well-prepared resources are waiting for us, because all of application stage is just the beginning stage. It's not so well saturated yet. So any kinds of idea based on the composite material structure is highly recommended to you. And the next lecture, we will close this lecture by addressing the recycle technique, something like that. Okay? So I'll see you tomorrow at the last lecture. Do you have any question about this? Do you have? Yes?
What kind of patterns we can follow to identify the application in real life? If we can see the slides, we can see the illustration, and we can imagine real life world, like I am moving through on the road and we are seeing that one vehicle is broken down. So how can I identify that this part can be replaced with the composite material so that it will serve the purpose? So how can we decide?
So you have already understood the three strong points by using composite material, right? Weight saving and intentionally anisotropic stiffening, right? And the next one is how it can be manufactured. So you know three of those. So that means I want to get more like one. Okay. Among part you are using these things. In that case, it's a weight saving product. It can give you much more benefit. Then you can think, okay, this part can be replaced by composite material part. Then what kind of a composite system is appropriate to that? Then you can start to choose. There are many choices. Okay. So the weight saving case among part you are using, or so I need more strong one. This part, this direction is very, the more strength is needed. Okay? But the other direction doesn't need it. But if you are using very strong, the alloy for the part, in that case, all the direction has the same strength. That means usually is supported this direction, only except this one. Then you can seriously think, okay, if I replace this part as the high performing composite material, then it will be enhanced. You can think like that. So weight and strength, directional strength is a good point you can think. Replace it by composite materials. It can be replaced, right? Right?
Important steps to take whether this material is sustainable or not for particular system. So what are the steps and how we can approach to get the sustainability of that particular material?
The sustainability means durability. Durability. It's the overlap concept, I think. So sustainability means we want to satisfy that product for a long time without degrading the function, something like that. Right? Yeah, performance. So sustainability. Sustaining environment for environment. So composite materials. So already, if you adopt composite materials rather than other conventional ones, you are already doing so at least 1 point. Because in manufacturing process, as you saw, the composite material has no waste. So there's no extra the waste material. But if you use the metal or other things, you need to get machining or there are many waste already. So that means using composite materials rather than others is contributing to environmental sustainability already. So next lecture you will think for full lifetime the cycle of the composite material is that to eventually contribute to environmental sustainability. Okay. You will talk tomorrow. Okay.
Sir,
yeah.
One more question. Please give me some idea about the photocurable elastomer resins, which can be 3D printable, biocompatible resin. Elastomers.
You asked the silicon, right?
Because I see in that slide.
So, what kind of the part can be of the goods by using the silicon-based one, 3D printed one, right?
Yes, sir, silicon-based.
So actually, after your question, I have not seriously think about it. I promise I will give the response tomorrow. Okay? It's kind of homework to me, right? I'll give you service tomorrow, right? Thank you very much. Today is Sunday, so tomorrow is Monday. So after the morning lecture tomorrow, in the afternoon, soon after that, I will leave for Korea, and I was very happy to together with you through this kind of introductory lecture series, and so whenever I give you the addressing, I think this is to a vastly wide range of lecture, because I just barely know the very simple part of it, because I'm computational guy. Computation, mechanical side, not material engineering or the aerospace engineering. I'm good at the mechanics of composite materials. So maybe I made some mistakes to share my information together with you. But whenever you have some question, even after watching my videos later, then feel free to send the email to me. Then I will study together with you to give you a good answer after that. Right? Thank you very much today. See you tomorrow.
Here once again I welcome you all in this tutorial session. So here we will see the working of the magnet stirrer, and also we will see the working of the ultrasonicator, and then later on we will talk about the filament maker, right? So this is the magnet stirrer, right? So here this is generally used to mix the filler particles into the polymer matrix. So suppose you have PLA, right, or you have ABS. So what we do is initially first we take the solvent, right? Solvent is what? ABS solvent is acetone. So we will take the grains of the ABS and we will mix it with the solvent, that acetone, and we will take the beaker, and then also we will use one magnetic bead, because this is magnet stirrer. So with the help of that magnetic field, it will rotate that bead, right? So I think Vivek is looking for the bead. So did you find? Yes. Okay.
Magnetic bead है. Suppose the downside there is a magnet. So magnet is rotating. So if you put a small similar magnet above it, so it will also start rotating. So if you put inside the beaker, the mixing will start. Suppose if I put that magnetic bead in the beaker, next. So mixing is getting started.
So usually this mixing is done for 2 hours, right? 3 hours, depending on the material and what filler we have used. So usually we have to follow the literature, right? What literature is recommending. Accordingly you can select the time, and also temperature is also very, very important. Because I want to discuss one of my case, because during my PhD I was mixing EVA and graphite, right, with the help of this magnet stirrer. So what happened, after one day, 24 hours actually, I checked whether they have mixed or not. So I found they were not mixed together. Why? Because I didn't go through the literature properly. So I found that the temperature, I should raise the temperature also. Then only it will mix, right? So then I found that temperature value. Then because here also there is a provision to increase the temperature, okay? So I kept around 60 degrees centigrade, and I just kept for 2 to 3 hours, and it was mixed. So sometimes these things happen, okay? So you have to be very careful while you are using the magnet stirrer and the filler and polymer matrix for mixing purpose. Okay?
So generally we use this mixing. This is a kind of micro mixing, wet mixing. In that wet mixing, we use this as a macro mixing. The purpose we use here, suppose we have a resin. We have resin whose viscosity is in between 150 cp centipoise. If we suppose we have to increase the viscosity of that resin, we can add that hollow glass microsphere that we have purchased from the market. With the increase of the weight of that hollow glass microsphere, viscosity will get increased. We can mix this using the magnetic stirrer. That is a micro kind of mixing. If we have to mix it at the intermolecular level, we can use that ultrasonicator. That one is probe sonicator. The probe means, but that one is a contact type. That probe will get in contact with the liquid. But another kind of we have there is a bath sonicator. Another sonicator, we have bath sonicator. So we can use that sonicator for micro level mixing. That is mixing at micron level. So we can use also that kind of mixing, sonicator mixing. सर इसका डेमोन्स्ट्रेशन के बाद the next demonstration बात सोनिकेटर micron level mixing. You can use that sonicator. We have two type of sonicator, that is probe sonicator and bath sonicator. The problem with the actually the probe sonicator is very accurate because it is directly in contact with the liquid. But the problem is that the probe is directly in contact with the liquid. It may react because it is in the form of metal and it may react with your liquid. So rather using probe sonicator, we generally use the bath sonicator because you take your samples in the beaker and you put your beaker inside the bath and there is no contact with the inside material in the beaker and outside the water. You can see here the bath sonicator.
This is Antara filter for the bath. To keep this beaker there. Stop this balance now.
So you just put your beaker like that and start the sonicator pass.
Button is there.
Button is this side.
फ्लूइड के अंदर वाइब्रेशन का डैम्पिंग नहीं होता
Switch on करेगा. इसमें नहीं वो तो बैठा था एक्चुअली वो है.
अल्ट्रासोनिक वो जो उसका सोनोट्रोड या जो
सोनोट्रोड इसमें नहीं है. वैसे नहीं सोनोट्रोड जो उसका
कोई बेस नहीं होता इसलिए वो वाइब्रेशन जनरेट करता है.
नहीं बेस तो आपने बना दिया ना ये अभी दिखाते हैं. चलो
साइज ही वैसा है. ये मेरा वो उसका जो काम किया
very simple vibrations, ultrasonic vibrations.
20,000 hertz of frequency of vibration.
In normal water. Which one? Which one there? On this side you have to do.
Generally we use deionized water in that bath. But we don't have facility in our department deionized water, so we use normal tap water. But after certain time if you use normal water, the scales will form at the side of the container. So it is prescribed to use deionized water. 7 to 8 liter of deionized water you can use. So the level should be, the liquid should be above that level. Above that level, then it will work properly. And you can see temperature control is also there and time control. And the frequency of this working is 20 kilohertz. So this is a non-contact type of mixing. So you can see the required material is not in contact with the outside environment. But in probe sonicator, you have to put probe inside the beaker so that vibration of that probe will mix the material. Both means probe sonicator is very effective if you see because it is directly in contact with your material. It is directly in contact with your material. Suppose beaker is there, you have to put a probe inside that beaker. In halfway you have to fill your probe in the liquid material. So probe will vibrate at a frequency of 20,000 hertz. So mixing will start. So that mixing will start. Here, water means mixing coming from the bottom. Water is vibrating. So that vibration is transferred to the beaker.
It is used for the micro mixing or micro mixing?
Micro mixing. This one is micro mixing. So the molecules will get in between the atoms, means in between the atom spacing. Yeah, you can use means nanoparticle also to mix here, but using this machine you can't do that. Magnetic. Yes. That will means magnet will attract your magnetic additive.
And we measure the homogeneity of mixtures.
Suppose you take initial sample, you dry it, and you do SEM imaging. And after mixing, you deposit the material, pour the material and dry, and cut it and put it under the SEM imaging. You can see that the mixing is homogeneous or not. That is the only way we see.
Right after the wet state, is it possible? The wet state is there in other than SEM?
The
wet state.
Yes.
For example,
it is in the wet state. Okay.
So, because say for example we have soricated it for 1 hour, we want to check it whether mixed or not, or homogenized or not.
So then,
other than that,
You have to trust the chemical.
yes, sir.
You have to trust the chemical.
Actually, we take the literature review. We take the help of the paper, already research paper work. We do. They use the same process. They use sonicated bath. After how much time they get the homogeneity? It can be 6 hours, 12 hours, even 24 hours also. One of the sample.
We don't have that much idea about the material chemistry, right? So if you refer good results related to the material chemistry,
What I was thinking is most of the time we actually extend the mixing process for a much longer duration than actually it is required.
that is right, because that is right.
Because there must be something by which we can see the homogeneity after 15 minutes.
That's why I'm saying, because we don't have that idea, right? So we just give paper of safety.
In our consumption studies, we have very different types.
Yeah.
We have the different dispersion.
GIAN actually studies that.
I have varied the time for 6 hours, then 9 hours, then 12 hours, and then up to 24 hours.
What was the observation?
For 24 hours, I got the better dispersion.
No, but I have read somewhere that there is actually an optimization value, and beyond that, it starts evaporation.
Yeah.
After 24 hours, is there any kind of homogeneity maintained, or when we achieve that same homogeneity?
I have been observed in this process. And for 24 hours, I got the best result compared to 12 hours.
Okay, this they improve after 12 hours.
There was fine dispersion of the nanoparticles.
But they cannot keep on improving in finite. So there must be some peak, and after that,
That's the it will decline.
Cost of.
You can go to the next one. Because we have
The next is 1.1 lakh rupees. This machine cost. That bath sonicator cost around 39,000, and that mixing
3,000 to 4,000.
4,000 to 5,000.
this is only 39,000?
39,000. Yes.
ये साइज पर ना इसका भी
इसका छोटे वाला इसे 10,000 वाला
बहुत छोटा मिल जाएगा इसमें तो आपको 10 20 में मिल जाएगा. You will find it.
ये इफेक्टिव है और मीन्स वेरी इफेक्टिव दिस वन इज, बट इट इज अ कॉन्टैक्ट टाइप. So
तो सेम ही है
कंट्रोलर वाइज देखे तो ये पल्स मोड है और कंटिन्यूअस मोड. लाइक पल्स मोड for 2 seconds the vibration will happen and 3 to 5 seconds it will stop so that cooling can happen. ये भी use कर सकते हैं. So that one is the probe, and we have other probe also have a smaller diameter. And placing के लिए since we have small beakers so we have customized the stand so that it get in contact.
And also we can vary that probe size also. Right?
Probe size, yes, we have two.
We have two types of probes.
So we put here our material and we should. दूसरे लग मतलब connected. Chemistry environment. People who are working in the material field, they definitely have this kind of sonicator, probe sonicator. In the bio lab also, in the chemistry department, they have this kind of probe sonicator. So the starting, how to start is, this is a power mode and this is the frequency you can see here, 25 kilohertz frequency. At that frequency, the probe will vibrate. And this is the run time and off time. So I have to set it, and this one is a pulse mode and continuous mode. Pulse mode means for particular time it will start and for some time it will stop. We use this just to cool down the probe because it will get heated if it will continuously vibrate. So pulse mode we use here. And the timer mode, suppose 20 minutes we enter, run time, on time 8 seconds. This one is in minute, this one is in second. So on time 8 seconds it will work. I should reduce it to 2 seconds, enter. And off time 5 seconds. Enter. And I should put it. See, mixing getting started. 5 seconds off and 2 seconds mixing. I can change it, depends on my material. So after after mixing it with magnetic stirrer, so you get uniform mixing of the material. Then now you have to go from macro mixing to micro mixing. So you can use this.
You use in steps.
Yeah, stepwise you have to use. Either use it with your hand, like mix it for macro mixing, because if you pour powder or some additives in the liquid, it will form at the top surface only. You have to mix it to get it uniform. After some uniformity will be there, you have to put it. You can use it under the probe sonicator for micro mixing. So this kind of thing is there. So with that mixing only, we mix the resin with glass microsphere and we put it in DLP 3D printer machine, and we printed dog bones. Yesterday sir showed that sample. We prepared from that probe sonicator and we printed it with DLP. That is a composite material. We used for application wise, we printed that for printing low dielectric constant material to use it in electronic application. Because in electronic, there is a conductive tracks is there. Below that, there is a dielectric material is there. So for ISRO project, we are preparing for dielectric material and conductive material. So this is the machine.
Some constant temperature.
Temperature, here temperature will vary. Temperature will getting increased. Means if you increase the time of vibration. Yeah.
This energy is ultimately getting it.
Vibration energy getting converted to heat energy.
So, for example, if at all the resin has a limitation,
Yes.
like it should not
So it may
cross
affect
up
the,
to
it
40.
may
It
affect.
will change the property
So
also sometimes.
we will be able to find the temperature on the screen.
No, not yet.
No, but that option is not available in this sonicator.
In this.
But it might be there. Okay. If you ask the manufacturer, they can just make for you that kind of.
Okay.
We have another one in another lab, but this is not having that.
Since we are in from mechanical background, we have contacted with other people who already used it from years. So they said that if you have to use probe sonicator, you put ice around it, so that temperature shouldn't get increased. So that is why we don't generally use this probe sonicator. We use bar sonicator for mixing. And this one is also contact type. Mixing is high, definitely mixing is very much high. Uniform mixing will be there, intermolecular mixing will be there, but the temperature, it will change the property of the material. Means high, if temperature will increase, your viscosity will get decreased, and temperature may change the property of the material. I was mixing resin. That initially resin was little bit yellow, but after mixing for 3 to 4 hours, it become brownish shade because of mixing. So mixing time means on time and off time is very important in probe sonicator. Like if you use 10 second or 20 second continuously, it will produce much heat. If you use it for 2 seconds, on time and off time is 10 to 20 seconds, it will reduce the temperature also. But you have to, your sonicating time should be high, so that the on time can be high. Like 2 seconds, you have to put it for 1 hour. So this is the mixing. Any question regarding?
Characterization of the composite materials. Do you have any idea about how these materials are characterized, and for which properties we characterize these composite materials?
Impact strength, flexural strength, mechanical testing.
Mechanical testing, that is tensile, flexural, bending, compression, right? These are the mechanical tests. Apart from that, we can test for their thermal degradation behavior. We can test for their dynamic mechanical behavior, right? And there are other non-destructive tests are also there. For example, if you want to characterize the voids or the structural changes after application of certain load, you can do the micro CT scanning of the composite material components to understand the internal structure of the composite material. So I will start with the from the basics, okay, because these are again very important. Especially testing of the composite material is easy, okay, but analyzing the result is very important. How you analyze the results and what is the conclusion after analyzing this particular result is very important. So we will start from the basic, the simple mechanical test, that is tensile test of the composite materials. So generally for the fiber reinforced composite materials or even the fabric reinforced composite material, we carry out the tensile test according to generally this D3039, ASTM D3039 standard. And in this particular according to this particular standard, we take a sample dimensions 250 mm by 25 mm, right? And cross head speed is 2 mm per minute. For
So what is this cross head speed?
cross head speed means what? So if you look at the principle of the this testing machine, it is tested based on constant rate of extension. So what is the rate of extension, rate of application of load on this particular composite material? So here, so you see that this is the bottom and top jaw in which the sample is gripped, and at this bottom jaw is fixed, whereas this top jaw will move, and at what rate this top jaw will move, that is the cross head. I think that is
It is variable.
it is
It can be varied.
It can be variable,
But in this particular standard, that is fixed.
in this case we generally test according to this particular standard. We test at 2 mm per minute. We can vary this test because in case of yarn, in case of textile yarns, the speed is very high. In case of other fabrics, the speed is again different. But in case of composite material, we test at very slow speed. So we call it as a quasi-static test because this speed is so small that it is approximately constant. So therefore we call these tests tensile or flexural at such a small rate. So we call them as a quasi-static tests.
Taking much more time.
Yes. It takes not too much time, especially the tensile test. It will not take more than 15-20 seconds. It will not take more than that. It will test. It will be the sample will fracture within 30 seconds. There is no problem. But in case of flexural test, it will take time. Flexural and compression test, it will take time. In case of flexural test, we have two different type of flexural tests. So you must be aware. One is 3-point bending test and another is 4-point bending test. So here is one picture which is shown. This is the example of 3-point bending tests. So here you see that there are two bottom support on which the sample specimen is placed, and this third point, right, which is attached to the cross head, right, it will move at certain rate, that is 2 mm per minute here, and it will bend this particular composite sample until it fails. So here one more terminology, that is span to thickness ratio. So what is this span to thickness ratio? So what is span? Span is nothing but the distance between these two bottom supports. what is the distance between these two supports is called as span, and
Thickness of the specimen.
how much is your thickness of the specimen. So if you look at the ASTM standard, this D7264, various span to thickness ratios have been given: 16, 20, 32, 64, and these span to thickness ratio has to be decided by based on how much is your thickness of the sample, and you have to choose it in such a way that the sample should fail at the tension side, that is from the bottom side. So when this specimen is loaded in the 3-point bending mode, the top side experience the compression, whereas the bottom side experience tension, tensile load, and the specimen should fracture from the bottom only. If it fracture at the top, this test is not considered okay. So the sample should the specimen should fracture from the tension side only, right? And you have to choose the span to thickness ratio based on that. That, for example, if your sample is very small, very thin, for example 2 mm thickness, if you are choosing 20 span to thickness ratio, so 2 into 40, it will be simply 40 mm. So if the span is only 40 mm, so it will be very difficult for such a small sample to fail at the tension side. So in that case, you have to choose different span to thickness ratio. So this span to thickness ratio is very, very important, and this is solid sample. So again, it is more easy for one to decide the span to thickness ratio. But if it is a spacer composite, which I have shown you yesterday, so in that case again the choosing the span to thickness ratio is again difficult. So you have to use some other standard for that particular case for testing. For spacer structures, the test standards are different. And the third test is impact. So in case of impact, as I said you that there are 3 different impact tests you can perform. One is ISOD impact test, where you place the sample vertically, and then the impact is the hammer impacts on the edge of the composite material, right? The second is in case of in-plane impact, so we place the sample composite specimen horizontally, and the impact is made on the edge. So that is again the Charpy test, which is called as Charpy test, and that is also in-plane impact test. And the third one is the out-of-plane impact test, that is drop weight impact test, where we place the sample right, and from the impactor hits on the composite specimen, and we measure the
impact. Choose the impact type test.
Yes, there is a guideline. So based on what is the mechanical performance required for particular application. For example, in case of automotive composites, so there are guidelines. For example, if you want to use any composite material for the dashboard, there are standard guidelines that how much should be the tensile modulus of this particular composite. It should be around 2.5 GPa tensile modulus. For flexural tests, there is again a guideline for particular components. Flexural strength, flexural modulus. Again, for the impact test, there are standards. So if you and suppose if there is some different type of composite material, for example, you want to use it in applications where the bending load is applied, or suppose compression load is being applied on the composite material. So in that case, you have to go for those particular type of tests. So again, one more. This is one of the again interesting tests you must be aware. This is the bearing strength of the composite material. So this bearing test is performed to understand the strength of the composite material under pinned joint. So because any composite material you are taking, during fabrication of that particular composite material, in actual application, you have to join it. And for joining, we use generally the pinned joints. And using this particular test, we can characterize how much is the bearing strength of this particular composite material under pinned joints. So there are various types of pinned joints. So you can have single pin, you can have double pin, you can have threaded bolt test, you can have this test without threaded, you can have this pin. So there is again this ASTM standard, that is D5961, and according to this particular standard you have to prepare the test specimen and you have to prepare the fixture to hold this composite material. So this is the fixture, right, test fixture, and this is the specimen which is held with the help of here one pin, and you have to hold this particular top side on the top jaw and the bottom, this specimen in the bottom jaw. And similar to tensile test, at certain rate, for example, you can take 2 mm per minute or any other rate, and you have to check how much is the load experienced by this particular composite material.
Facilities available in the particular.
Yes, we have fabricated our own fixture. It is simply the fixture, there is nothing else, and you can also fabricate your own fixture, there is no problem. So if you look at this particular fixture, you can prepare the fixture using metals also, or you can prepare this fixture using composite materials.
For loading means again the tensile machine will be used, right?
Tensile UTM, simple UTM machine.
And do you have the facility for all these 4 types of tests, tensile, flexural, and
we have facility for tensile, flexural, but we do not have right now for the impact test.
okay?
And
what about the bearing structure?
Low velocity impact.
So we have that drop weight impact test, but not the ISOD or CHARP impact testing facility right now here. So this is again one of the interesting tests, and I will show you how the next test is thermogravimetric analysis. This you must be aware about this test. This particular test is carried out to understand how your composite degrades with temperature. And here is just one example we have given for any that, for example, if it is a cotton epoxy composite or a glass epoxy composite or basalt epoxy or Kevlar epoxy type of composite, you know, epoxy generally degrades around 300 degree, 250 to 300 degree degrades. But since if you want to find out, suppose let's say you want to find out the behavior up to certain, for example, more than that epoxy degradation temperature you can carry out, and it is generally we do this TGA under nitrogen atmosphere. Why? Simply to avoid the oxidation of the sample. Otherwise it will degrade earlier. In nitrogen atmosphere the oxidation will not take place and it will degrade slowly compared to your without nitrogen, and at certain rate. So this rate you have to decide. For example, it can be 10 degree per minute. You can have the rate of increase in temperature within that particular chamber.
Does this rate affect the test result? Or
yes, this rate affects the test results, because test will give you how much is the change in the weight of the specimen with temperature.
with respect to yes.
So this rate again, it influences the change in the weight. Suppose the rate is higher, for example 30 degree per minute, so the composite may degrade earlier. And the next, again, one important test is water absorption test. If your composite is, let's say, natural fiber reinforced composites, in that case you must test it for the water absorption test, because natural fibers are hydrophilic in nature. They absorb the moisture from the atmosphere, and once if they absorb the moisture, it will directly influence the interface with the matrix, and it will lead to change in the it will lead to decrease in the mechanical performance. And this is the one of the tests known as ASTM D570 using this particular standard. So how the sample is tested using this standard is, you can simply take the specimen, right, take the weight of the specimen and simply dip in the water. You can use tap water or you can use some distilled water also, that is up to your choice. And after every 24 hours You have to remove the sample. You have to remove the excess water using tissue paper and take the weight of the sample. Again put it in the water. Again check it until you get no change in the weight, until the saturation takes place. And then after saturation, so that is the saturation time. So that may be for some samples it may be 1 or 2 days. For some sample maybe 30 days, 40 days. So it is a long test. Suppose it is, for example, we have done using for the cotton epoxy composite. It took us 30 days. Sometimes it takes more than that. You can test this particular natural fiber composites or even the glass epoxy composites for this water absorption test with water at elevated temperature. You can simply take a kettle, right? You use the hot water, right, and you set the temperature of this particular kettle, and you put the sample. And after every 24 hours, you measure the change in the weight. So you can understand.
In that case, how will you maintain the temperature of the
So you have to take a kettle with temperature. You can controller, temperature control. So in that case, you can do it very easily. And if you want to test, let's say, change in mechanical performance after water absorption. So for that, you have to use simply what, let's say you want to test the tensile properties or flexural impact properties. You take a specimen of that particular size and you put in a water. And do this experiment, means checking the weight after every 24 hours until the compound saturates, and then after saturation you simply test it and you check the mechanical performance. So in that case, so in this way you can identify, you can characterize mechanical performance after saturation with the water.
What application this test is very, very important?
So for the outdoor applications of the composite material, because today lot of people are talking about the natural fiber imposed composites, and they are saying that these are the green composites because natural fibers are there, even though the matrix is synthetic, I mean the polymeric matrix. So for the outdoor applications of such composites, you need to do this particular test. And but one more important thing is that you will experience, if you do this particular test, you will experience that if you change the specimen size, your results will vary. Suppose you are taking a 5 by 5 centimeter sample and you are checking the water absorption, and if you are taking a little smaller sample or little larger sample, for example 10 by 10 centimeter sample, you will get different results, completely different results. And you therefore you have to choose only one size of the sample for if you are doing multiple tests, right, for the different type of samples, so the size should be same. Otherwise the water absorption result will be different. And so if you look at this particular plot, this is the plot of fiber volume fraction, effect of fiber volume fraction on the tensile strength and modulus of the composite material. So once you have got these results of the tensile strength and modulus, comparing the results of the material becomes difficult, when you have simply the results in the, let's say in the Newton, you have just breaking load in the Newton, so you cannot compare it. So therefore you convert it into the stress form, but even those values are difficult when you want to compare with some other material. So therefore you can calculate the specific tensile strength in that case, that is the tensile strength divided by the density of the material, or you can normalize it by dividing with weight of the composite material. So it will give you more appropriate idea about the mechanical performance of the composite material, and the results will become comparable. Similarly, in case of flexural strength or any other test, so you should try to find out the specific mechanical properties, and then only it will be more easy for comparative analysis. In case of tensile tests, look at this particular composites. These are the composite specimens fractured under tensile loading. You see that how these particular composites are fractured, whether it is a straight line of material separation or is it a wavy. So this is also again approximately straight, this is also approximately straight, or sometimes you see the composite material fractures with waviness at the line of separation. This will give you an idea about how your material reacts to the tensile load. Right, at different speeds also you can carry out this particular test and identify this particular material behavior and why this. So there can be various reasons why the material is separated exactly approximately at the straight line and why it is not separated with, let's say, waviness. So that is again one of the point which should be investigated. Under this flexural tests, for example, you see, as I said you that under 3-point bending, the top layer experience the compression, bottom layer experience the tension, tensile load. And if you look at this particular composite material, this is the cotton epoxy composite and this is the polyester epoxy composites. So this is the recycled cotton epoxy and this is the again recycled polyester. You see that cotton epoxy composite, you can see the fracture of the material at the tension side, but in case of polyester there is no fracture. There is no fracture, and the reason behind this particular thing is, you know, the polyester is more flexible. It has more elongation at break, around more than 20% elongation at break. Polyester fiber sometimes have. So in that case, the composite material you can get more elongation at break, and therefore it will not fail. So when you are designing a composite material, even you may think that it is epoxy, so it should fracture, right? But it is not fracturing. So if you are engineering any composite material, deciding the fiber material again is very crucial based on what is the application of that particular composite material. This is the same image. Again, you must be aware about the scanning electron microscopy of the fractured specimens, right? And we try to understand how effectively how effective is your you know, the how much is the fiber matrix interface, and you can find out how your fibers are actually fractured in the composite material, whether there is any fiber matrix debonding or fiber pull out. So fiber pull out is an indication of poor fiber matrix interface. So
do you have SEM facility, sir?
Yes, we have SEM facility at the central instrumentation center. Yes. This is the result of water absorption of cotton epoxy and polyester epoxy composites. So in the water absorption test, we generally measure these two properties. That is equilibrium water content, that is how much is the maximum water this particular composite can have at the time of saturation, and another one is the diffusion rate. At what rate your composite is absorbing the water. So these are the, again important. And as I said you that if you see that when natural fiber absorbs the water, it swells, and because of this particular swelling, it will directly lead to you can say it will directly affect the interface between the fiber and matrix, and therefore the mechanical performance of this particular composite material deteriorates. So you see that again.
So after conducting this test, we can again go for the mechanical test.
We can go for. So we have done it. So we have done it for this particular composite material. So you see that for the dry cotton epoxy composite, the material fractures under flexural loading, but after water absorption, it becomes flexible. It becomes flexible, and it do not. We do not see this crack at the tensile side of the particular composite material. So this is the result of this weaving response of the cotton epoxy and polyester epoxy composite material. So you see that how we have analyzed this particular result. So So when any composite material fails under this particular bearing load, it fails with different types of failure modes. Let me tell you first. So the material may fail in a bearing mode, or it may fail in a cleavage mode, or net tension mode, or maybe shear out, or maybe the tear out. So these are the various failure modes. You see that. So here you can see the shear out mode. Here you can see the net tension mode. So why this particular composite has failed in the shear mode, or why this composite has failed in the net tension mode? Because you see that bearing or shear out mode is more preferable, because it is the reinforcement is actually taking the load and it will sustain that particular joint, right? And these are not good actually, the failure modes.
This is not desirable.
This is not desirable. So how to improve the performance in the bearing? So you only by changing the reinforcement structure you can enhance these are the fiber reinforced composites, simple fiber reinforced composites. If you go for fabric reinforced composite materials, it will give you more bearing strength, and it will fail majorly in the bearing mode and not in this cleavage or net tension or tear out mode, because of the as I've shown you yesterday, the oven fabrics, you have interlacement in the warp and weft direction, right? And because of this interlacement, it will not allow that particular specimen to break in the net tension mode. So if you look at this analysis of this particular test, you see that how we are analyzing it. On the x-axis we are plotting the strain, on the y-axis we have this bearing stress, and the other y-axis we have rate of change of load with the strain. So if you look at this particular plot, there are generally 4 regions. So this is the first region, so this is the stabilization region, followed by the elastic region, where you will get a straight line of this particular bearing stress and strain curve, followed by this pre-net tension zone, where the actually matrix crack extend, and finally the composite will fail in the net tension here, right? And this red plot, it shows the change in the load, dP by dL, that is change in the load per unit change in the extension. So how this particular joint is experiencing the load. So you see that up to certain point it takes the load, but after that better, you can say bearing strength, and they are failed in almost in a shearing mode, whereas these are cotton and jute epoxy composites, so therefore they are failed in bearing mode. Thermogravimetric analysis, so these are the typical plots you see in the TGA analysis. One is the weight loss with temperature curve, and another is the derivative weight loss. These 2 plots you get. So this plot will show you, so you see that on the y-axis you have weight, on the x-axis you have temperature. So with increase in the temperature, how much is the reduction in the weight of the composite? So 100 means the initial weight of the composite material, and with the increase in the temperature, how your composite is degrading, and at what temperature actually it will show you the very high change in the temperature. So this is the region, this is the temperature region, for example this 300 to 400, where we can see the maximum reduction in the weight of the composite material. So you can say that our composites, this particular composites, these are the cotton epoxy composites, these are thermally stable up to 300 degrees centigrade. You can see that there is a very, very small change in the weight of the composite material up to 300 degrees centigrade, and they are thermally stable enough up to 300 degrees centigrade. If you look at this derivative weight loss, so this particular plot you will get on the x-axis temperature, on the y-axis percentage change in the weight per unit time. So you see that again up to 300 degrees centigrade, the change in the weight per unit time is very very small. The rate is very very small. But after this particular temperature are up between this 300 and 400 degrees centigrade, the weight, so the rate of change in the weight is very very high, and therefore only you can see that the reduction is very high in this particular temperature range, 300 to 400 degrees centigrade.
Weight loss occur due to the erosion of the component.
Degradation of the materials.
Because of
In
the
which
temperature.
form? Degradation. In which
Melt
form?
and vaporize, right?
It degrades. So degradation means what you can say. It can melt. It can, for example, if it is a polymer, it will melt and evaporate. And at the end of the test, the component which will not evaporate, they will remain as it is, as a ash. So this is what here. So it will remain as ash. So it will not be zero weight. There will be certain component which will remain as it is, and therefore it will not be zero. So this is called as final the ash of this particular composite material or any polymeric material that you are testing for this particular test.
In case of DTG, up to 300 degrees centigrade it will become stable. The rate is stable. But and there is a downward curve. Again it gets pulled back and then it becomes stable. So
Right.
that
So,
so
so this may be because this is because majorly if you see that the weight is reduced here, but this may be because the ash content, maybe because of the ash and in this particular
whatever the residues remain,
residue remains.
it reflects
It reflects. That is what
stability
it is.
after I think 500 degrees centigrade later on.
Yes, this is what.
It initially becomes a negative derivative and then again it
becomes positive. Yes. This is the typical curve you will get in every case.
Yes,
In every case you will get this.
The nature remains same.
Nature
Only the temperature difference.
will be there, but the shape of the curve will
Yeah.
be same.
Yes.
So I have one note, sir. Whether you said that it is stable up to 300 and it is coming down almost 20 rate.
Huh.
So whether that is the melting point of the composite that we are testing, 300 degrees Celsius.
Here,
Yeah.
Major weight loss happens from 300 degrees centigrade to 400 degrees. Major decomposition of that material. Yes, sir?
so at this particular, this is the on-set temperature. From this on-set temperature means what? The temperature from where actually the sudden change in the weight of the material takes place. So this is what it is, and we also measure the 5% weight loss temperature.
Yes.
That at how much temperature there is a 5% weight loss. So look, there are so many things people show in the research papers, right? But we have to see what exactly is required for our application. Whether, for example, you are using this composite material for the railway application, for example, or aerospace application, or any other material. What is your requirement? What
We
is
also
your
having this
requirement?
facility, sir, in our institute.
TGA analysis, it is not available. It is not available in the institute.
In certain cases, the polymer fabric which we are using, that may be reactive to the skin. How long you are wearing that, just like epoxy or terylene, that may not be suitable for a particular kind of persons. So there is
These are composite
there are
materials, but not fabrics.
Okay. There is some test available which can judge that skin irritation test or something like that.
Yes, these tests are available, but they are for the fabrics. These are
In our institute, that tests are available.
no, these tests are not available. But you can, but this is actually the thermogravimetric analysis of composite material. You can do this TG analysis of any material, and let me tell you once again that this. So depending upon the application, we have to decide that how much up to how much temperature this particular material is stable. And let me tell you one more important thing is that, we say that we can use this epoxy composite, etc. But we have to, again, one more thing we have to analyze, that is what are the emissions during the burning of the composite. For example, let's say you are using this composite in a train, and suppose there is a fire accident takes place. So if this particular material is generating dangerous smoke, then it is highly hazardous. So you have to, so there are certain
Evolved gas analysis. Evolved gas analysis we have to do.
Yes.
We have to take the out from the DAC and we have to analyze the gases which is coming out of the DAC.
But there are today you have some TGA, this thermogrammetric analyzers equipped with gas analysis.
Yes, sir.
Integrated. So integrated machines are there, so you can analyze the gas, and based on that you can do this. So another one more test here is the compression test of sandwich composite structures. So you can do this particular compression test for sandwich composites if your application is like that. For example, you are using honeycomb composite or any sandwich composite in the flooring, or any such application where it is experiencing the compressive load. So for that particular test, for that particular application, we have to do this compression test. And again, the test standards are different. ASTM D 365 and 364. These are the two standards basically for the compression test of the sandwich panels. And in this particular test, we actually measure how much is the energy absorption of this particular composite material, and how this particular composite material is actually failing. So I will show you one plot I have with me. So let me show you that. So you will get an idea about how this so you look at this particular plot. So this is the again same honeycomb structure, honeycomb composite material under compression load. If you look at this particular plot, deformation, force deformation plot, you will see the four regions. First is the elastic region, where this is the your Hookean region, where you will get a straight line, right? Then followed by the yield stage, followed by the yielding. Then there will be a region where approximately no change in the load will take place. So your material deforms, but the load remains approximately constant. And then followed by the compaction stage. Compaction stage means the densification of the material will take place, and then therefore only the load experienced by this in this stage is more, because the densification has taken place. So this is the typical plot you get in the compression test of this sandwich panels, right? So and you can find out the energy absorption. So you can find out generally for the comparative analysis, we do this, we find the energy absorption within the Hookean region, within this, where we get a first peak.
Okay.
So we find out
Maximum.
the area under this particular curve up to the first peak, and this is, we find out the energy. Again here, finding energy is very easy, but analyzing of the energy for different type of specimen sizes, right, it is different. So for that we have to measure the specific energy per unit volume or energy per unit density. So these type of composite materials, honeycomb, I think I have shown you this or not. So this honeycomb, these are used in the helmets because they are very high energy absorbing materials. So you see that this is the hemp fiber. So this is the honeycomb fabric made out of the hemp fiber and their composites. And this is the Kevlar. This is the honeycomb fabric made from the Kevlar and converted into composite material. Okay? So that's all about this this characterization of the composite material. If you have any doubt, please ask.
BSc analyzer is working or
This I don't know exactly, but maybe in the working.
And what is this question?
This is TGA, thermogrametric analyzer.
TGA.
TGA. Any
Where
doubt?
we put the sample inside this
So-
machine?
The chamber is here, so in this particular chamber we place the sample.
If I need to find the melting point of the composite material, I will put it in DAC and I will heat it up to maybe 600 degrees. So suppose it is epoxy resin and a fiber, glass fiber. So whether it will melt separately, whether I will get 2 peaks or will be 1 peak.
No, look, the thing is that you are the epoxy resin after curing you cannot melt it. After curing you cannot melt it. Let me tell you very important thing. You may be buying any epoxy resin from the market. How to find out the curing temperature of the epoxy resin? So you can find out this curing temperature using the DSC.
Yes.
You simply take the epoxy resin and the hardener in proportion of this epoxy resin, mix it and do it, place it in the DSC. You will get the downward peak. That point is your curing temperature of that particular epoxy. People generally do mistake. What they do, they generally take any epoxy resin, they mix it and simply cure at any temperature given in any research paper. But that is wrong. So you will not get a good mechanical performance if you do like that. So you have to do DSC, then only you will get a correct curing temperature for this particular epoxy. Right. Okay, thank you very much.
Thank you.
Thank you very much.